So we have seen electric field calculations because of different charge distributions like point charge, line charge, and surface charge, and the same approach can be followed for the volume charge also. But all these things we have done using the Coulomb's law method. Okay, Coulomb's law is actually giving the force. From that one only we got the electric field equation, so that we can able to tell that E bar is equal to 1 by 4 pi epsilon q by magnitude of r square into r cap. That method we have followed till now. Okay, and the same calculations, that means the electric field intensity due to point charge, line charge, surface charge, and all these things can be obtained in a simple manner by using the Gauss law. Gauss law is very important. So using this Gauss law, we can able to calculate this electric field very easily. But there is a condition to apply this particular Gauss law. What is that condition means? Symmetrical distribution we have to have. Symmetrical distribution of flux we have to consider, such that we have to take one Gaussian surface. Okay, so Gaussian surface is actually not a physical surface. It is imaginary surface. We are considering that one. It is imaginary surface. We have to select this imaginary surface in such a way that the flux lines are going through this particular surface symmetrically. That is the condition. So if you follow this one and if you apply the Gauss law, calculation of electric field intensity is very easy. Okay, so we are going to see that one. So before going to see the problems, first we have to understand what is this Gauss law. Gauss law is available for electric fields and also for magnetic fields. And here itself I will give the equations. So for electric fields, we have the Gauss law like this. Closed surface integral of d bar dot ds bar is equal to q enclosed. And this itself can be converted into another form called point form or the differential form, that is del dot d bar is equal to rho v. And for the magnetic field, the Gauss law is given by closed surface integral of d bar dot ds bar, it is equal to 0, and this itself can be converted into point form or the differential form like del dot b bar is equal to 0. Okay, now we are going to deal with this particular Gauss law. For the electric fields, whatever the Gauss law is there, first we are going to see that one. Okay, so we have dealt with till now E bar, now we are going to see D bar. Okay, it is electric field intensity, it is electric flux density. That means electric flux per area. That is electric flux density. So electric flux is measured, electric flux psi E is measured in coulombs. That means what we have coulombs for another physical quantity also we have coulombs as a units. What is that one? Charge. Okay, Q is the charge. For charge we are using the units are coulombs only, and for electric flux also we are using coulombs only. Both are having the same units. Okay, both are having the same units. So how much amount of electric flux is passing through a surface? Okay, that is defined with respect to this particular electric flux density. So electric flux density means magnetic flux per area, per unit area, how much amount of electric flux is passing, that is given by electric flux density. So coulombs per meter square are the units of d bar. Okay, similarly here itself I will define the b bar, then it will be convenient to you to understand that one. Okay, so electric flux density means electric flux per area. So magnetic flux density b bar is nothing but magnetic flux per area. So electric flux is measured in coulombs, so that's why coulombs per meter square, and magnetic flux is measured in Webers. So Webers per meter square. And Webers per meter square can be taken as the another unit called Tesla. So you can use that one also. So anyhow, you come to this electric fields Gauss law only. Gauss law for the electric fields only. So listen carefully. Understanding of this one is very, very important. So see carefully. You assume one room is there, and all the rooms are all the walls in that particular room are having same dimensions of the same dimensions. So for room, that means that room is in the form of the cube. Okay, so all the walls are having the same directions. So in that particular room I have some charge q is equal to I have 6 coulombs of charge is available, and I know that charge and electric flux, okay, electric flux both are having the same units, that is coulombs only. So whatever the charge flux lines are coming outside, this is nothing but electric flux. What is coming outside? Okay, so electric flux is also measured in coulombs, electric charge is also measured in coulombs. So in that particular cubical shaped room we have 6 coulombs of charge. We have 6 coulombs of charge. Now because of this charge, all the electric flux lines are going outside. Because it is the positive charge, all the electric flux lines are going out of that particular room. So we can take like this, all the electric flux lines are going outside. Now the question is, how much amount of electric flux lines are going outside, okay, through the surfaces of that particular room? Means the capacity or the charge available within the room is equal to 6 coulombs. 6 coulombs of charge is available within the room. So same amount of charge can be going out of that particular room only. So what is there inside, okay, it can able to go outside. So 6 coulombs is available inside, so 6 coulombs can able to go outside, This is totally maximum amount of electric flux can able to go out of the room is equal to 6 coulombs only. But left side whatever I have written 6 coulombs, this is the charge. Okay, this is the charge. But right side whatever we have written, that is in the form of the flux. That is in the form of the electric flux. Psi e. This is the psi e. Okay. So in order to get the same equation, I am taking this 6 coulombs, that is electric flux on the left side. You can take right side also. This is not that much big deal. You can take anywhere. So 6 coulombs of charge we have, that is q. So in the room I have 6 coulombs of electric charge, so that through the surfaces of that particular room I can able to have total 6 coulombs of the electric flux can able to pass through that one. Now instead of having, I said that that room is in the form of the cube. That means all the 6 surfaces are the 6 walls of that particular cubical shaped room are having the same dimensions. Okay, so now the question is, through all the 6 surfaces, if you measure the electric flux, that is equal to 6 coulombs. But now I am asking for each wall how much amount of electric flux is passing. Okay, for each wall how much amount of electric flux is passing means only 1 coulomb of electric flux is passing. Okay, 6 walls, so 6 into 1, that is 6 coulombs of electric flux is passing. Okay, because that's why I have taken all the walls are in the same direction. So through each wall we will be having 1 coulomb of electric flux is passing. Through all the 6 walls we will be having 6 coulombs of electric flux that is passing through the total Q. Okay, so this is what you need to understand carefully. Okay, so whatever I have explained now, this itself is Gauss law. Now whatever I have told in words, that we have to give in the mathematical form. Then you are going to get that equation, closed surface integral of d bar dot ds bar is equal to q enclosed, and that can be converted into del dot d bar is equal to rho v. But first of all you have to understand this one. How much amount of electric charge is there within the room, same amount of electric flux is going outside. Okay, we are equating charge available inside the room that is equal to electric flux going out of the room. Okay, these two we are equating. There is no necessity to have the positive charge only inside the room. You can have the negative charge also. You can have the combination also. You have several charges including line charge, surface charge also may be available within the room. So how much amount of electric flux is going outside, that much amount of electric charge is available inside the room. So that is simply we can able to tell this is the Gauss law for the electric fields. Okay. Now we will continue the discussion on the electric fields now. Okay. So I will take the new page here. Okay. So what did I say? Here, whatever the electric flux that is passing through the closed surface, total surface, through all the 6 walls if you take, then only that is equal to total charge available uh, within the that particular room. That means closed surface, enclosed in a closed surface. Closed surface we have to consider, because if you consider only one wall, that means open surface. You see here, so this is the closed room. Within this particular room, I have q coulombs of charge. So if you consider all the six surfaces, then only you will be having q coulombs of electric flux is coming outside. Okay, this is through total room. That means technically we can say this is through entire closed surface. This is through entire closed surface. But if you consider only one wall, q by 6. Through only one wall. That means only one wall means technically we can say it is open surface. Through only one open surface, we will be having the electric flux. How much amount of electric flux is passing means q by 6. If you take two walls, two open surfaces, you will be having 2 q by 6. Okay, 3 q by 6, 4 q by 6, 5 q by 6, 6 q by 6. That means 6 surfaces means we are considering the total closed surface. Okay, total room we have considered. So q amount of electric flux is passing through that one. So this is what we have to analyze. Okay. But what is this Gauss law is saying? If you consider the closed surface, then that is exactly equal to electric charge only. How much amount of electric flux is passing means that is exactly equal to electric charge only. So this itself is our Gauss law. Now we are going to modify this particular equation. Simply Gauss law is nothing but first equation you can able to write this one only. So net electric flux passing is equal to total charge enclosed by that particular closed surface. So in words what we can tell, the net electric flux passing through any closed surface is equal to the charge enclosed by that closed surface only. Like that we have to tell. But this electric flux now we have to tell in terms of the electric flux density. Electric flux density. Now you assume this is one closed surface. This is one closed surface. So we have taken, instead of considering the total closed surface at a time, we will take one differential surface like this. This is one differential surface, and already I have mentioned that differential surface direction or the any surface direction is perpendicular to it. Okay, surface direction is perpendicular to it. So this is ds bar. Okay, so and its direction is given in the normal direction, like normal direction to the surface. Okay, so this through this particular differential surface, certain amount of electric flux is passing. So that is given by d bar ds bar. You see, I need to get how much amount of charge is, how much amount of electric flux is passing through only this particular differential surface ds. Closed surface is the entire surface. But instead of taking the entire closed surface at a time, what I am taking? I am taking only certain differential surface. So through this particular differential surface, how much amount of flux is coming means, so you see here with respect to units, coulombs per meter square, flux per area into area. So what you will get to coulombs, that means it is electric flux psi e. So to get the electric flux psi e, which is passing through the small differential surface ds, so you have to take the product of d bar and ds bar. But in the textbooks, if you see, here you will be having the dot product. So you need to understand here why the dot product is used. Okay, so many people will tell what is Gauss law means closed surface integral of d bar dot ds bar is equal to q enclosed. But you need to tell the significance of the dot. You need to tell the significance of dot. So here we have understood that anyway product is required. Okay, product of d bar and ds bar is required. But why do we need here dot product? Dot product means once you expand this dot product, then you can able to understand. So d bar dot ds bar is equal to magnitude of d bar, magnitude of ds bar, and cos of the angle between these two. That means d and ds. So what is ds? Whatever the surface we have taken, that one, that is coming outside. Okay, that is coming outside. Now you see carefully. You assume this is your screen, and from the screen you are getting the electric flux lines towards you, towards you. So whatever the perpendicular direction is there, that means this is the small ds value, whatever we have taken in the previous diagram. So you assume this is a ds. Through this ds, you are getting the electric flux lines towards you. Okay, towards you. So to measure that electric flux lines, if you take, okay, the electric flux lines are coming out of this particular screen towards you. So you need to keep this ds also in the same direction. Okay, for example, here I will show in a different manner if you can't able to understand this one. So electric flux lines are going this way. Electric flux lines are going this way. What you are doing in the sense, you are keeping the differential surface like this. Electric flux lines are going in this way, but this differential surface is this one. What is the direction of the differential surface? It is coming out of that particular surface, perpendicular to the surface. So here what is happening? No electric flux lines are going into the surface. Okay, this is the surface you have to consider. No electric flux line is going into the surface. So when it will go? When it will go in the sense, if you keep your differential surface ds like this, then how you have to consider in the sense like this. Okay, like this we have placed, this is equal to this one, then electric flux lines are going like this, going like this. In this manner you have to consider. Okay, so what we can able to tell, when the surface is like this, what is the direction of the surface? Towards this side, perpendicular to that one. So electric flux lines are also going in this direction only. Okay, but when the electric flux lines are going in this direction, okay, when you keep the differential surface in this direction, okay, what is the surface direction? This way, but electric flux lines are going this way. So in this case, all the electric flux lines cannot be catched by the surface. Okay, all the electric flux lines, maximum number of electric flux lines cannot able to go in this case. But in this case, all the electric flux lines can able to passing through the surface. So once again I will repeat that one because it is the first time we are dealing with the dot product. So see carefully. This is the surface ds, but we can't able to understand in this manner. So you rotate that one. So this is the side view of the surface. Side view of the surface. Okay. So what is the direction of the surface? Perpendicular to this one. So this is the direction of the surface. Okay. Now electric flux lines are passing in this way. So what I can tell? All the electric flux lines are passing through this one only. That means d bar direction is also in this direction only. Okay, d bar direction is also in the same direction. In which direction? Ds direction only. Okay, whatever the surface direction is there, in the same direction d bar direction is also there. So that in this particular case, maximum number of electric flux lines are passing through the surface. Now you are keeping the differential surface like this only, in the similar to the previous case, ds n bar. But now electric flux lines are not passing in the same direction of the surface. Now the electric flux lines are passing in a direction which is making certain angle here, So this is the d bar direction. This is the electric flux direction. So in which case we will be having more amount of flux passing through the surface in this way. This is the first case. In the first case we will be having more amount of flux passing. When you have the third case is this one. So again we are fixing the ds direction. ds is like this only, but now electric flux lines are passing in this way. Okay, exactly perpendicular to the surface direction is this one, but electric flux lines are passing in this way. Okay, d bar direction is in this way. That means here theta is equal to 90. Okay, so when you take theta is equal to 90, what is happening? The net electric flux passing through the surface is equal to 0. The net electric flux passing through the surface, the psi is nothing but surface is electric flux is there, but we need the electric flux passing through the surface. So that is equal to 0 here. But in the first case, maximum amount of electric flux is passing. That is exactly equal to how much amount of charge is there inside the closed surface. Actually here you have to take closed surface like this. And in this case, what is happening? Not maximum, not zero. Somewhere there in the middle. That means it is exactly following cosine-saddle signal. Okay, cosine-saddle uh, phase, cosine-saddle values it is following. Why? Because you see here the direction of d bar in the direction of ds bar both are same. That means here theta is equal to 0 degrees. Okay, when you have theta is equal to 0 degrees, maximum amount of flux is passing. Okay, so cos 0 is 1. But when you have theta is equal to 90, cos 90 is equal to 0 you are getting. Cos 90 is equal to 0 you are getting. Okay. And in this case, cos for example 45 degrees, that is equal to 1 by 2. That means in between these two. So it is exactly following the cos function. So there is a requirement of the multiplicity and this cosine side also. So all these things will be available in the dot product only. So d bar dot ds bar is that is the requirement of the dot. That is what I need to tell. So it depends upon whatever the net electric flux passing through the surface. It is not only depends upon the product of d bar and ds bar. It is depends upon the angle in between the flux direction and surface direction, whatever we have taken. So it depends upon the direction also. That's why, and that is following the cosine rule. That's why we have to take here d bar dot ds bar. But it is giving this d bar dot ds bar is giving only this small differential surface only. But we have to consider entire closed surface. For that purpose, we have to take closed surface integral of d bar dot ds bar is equal to that net electric flux passing through entire surface is equal to total charge available within the closed surface. So this is called our Gauss law for the electric fields. Okay. So this is the explanation for this one. Now we will continue further concept of this particular Gauss law. Okay, now what we got? Closed surface integral of d bar dot ds bar is equal to q enclosed. Like this we got q enclosed. Okay, so now this charge in the previous class we have calculated this total charge using this integral rho v dv integral rho s ds like that. So when you have point charge, this is okay within the closed surface. If point charge is there, that is okay. But you may have line charge also. So how to get a dq through the line charge dl rho l dl? Already we have seen this one. Coulombs is equal to dl rho l means coulombs per meter into meter. So coulombs will be coming. So to get the total charge, what we need to do? Integration. So integral rho l dl. Similarly, q is equal to, we can write integral rho s ds. And here we can able to write integral rho v dv. So this thing can be written as integral rho v dv, volume integral of integral rho v dv. Like this we can able to write. But now if you see carefully, left side surface integral is there, right side volume integral is there. Okay, so now very important point I am telling. Closed surface means like a room. If you take all the six walls of the room, that will become closed. If you take 5 4 3 2 1 anything, that is called open surface only. But if you take the all the six walls of the room, that is called closed surface. Closed surface means it is providing the volume. So here you can able to see left side part is closed surface integral, right side part is volume. So it is following this one. So we have in mass one thing is there, that is closed surface can be equated to volume by having the Gauss divergence theorem. So by using this Gauss divergence theorem, we can convert closed surface integral of any vector can be written as volume integral of divergence of that vector. This is possible. Okay, from the Gauss divergence theorem we can able to convert the surface integral into the volume integral. The closed surface integral of a bar dot ds bar is equal to volume integral of divergence of a bar. Okay, it is not simply a bar, it is divergence of a bar. So this left side part, whatever we have written here, that can be converted into volume integral now using this particular Gauss divergence theorem. Okay, so before going to apply this one, the similar to this particular Gauss divergence theorem, we have this Stokes theorem also. So now you see Gauss divergence theorem is applicable whenever we need a closed surface and volume. Like this, if you have, we can able to go for the Gauss divergence theorem. But when we have open line, another open line, now if you take like this, it will become closed line. So closed line, if you take now, the surface has been created. So when you take the closed line, that is equivalent to open surface. Okay, what type of surface? open surface. So you see here, closed surface is providing the volume, but closed line is providing the open surface. So for this purpose, in order to convert the closed line integral into the open surface integral, we are using the theorem called Stokes theorem. So these two are very important to convert the integral form of the Gauss law into this point form. Okay, and integral form of the Ampere's law into the point form, we are using this Stokes theorem. So what we have here, closed line integral of a bar dot dl bar, this can be written as open surface integral of del cross a bar into ds. Like this we can able to write. So here curl of a we are taking, here divergence of a we are taking. So to convert closed line integral into the open surface integral, we are taking in this manner. Okay, closed line integral of a bar dot dl bar is equal to open surface integral of del cross a bar ds. Okay, so anyway, now we are not going to use this Stokes theorem for the time being. We are going to use this Gauss divergence theorem only. So using this Gauss divergence theorem, what we can do? The closed surface integral can be converted into closed surface integral can be converted into volume integral. So I am applying this one to this closed surface integral of d bar dot ds bar. So what we will get? Volume integral of del dot d bar. So like this we can able to write this particular closed surface integral I have written as a volume integral. Now right side part as it is, we have here this volume integral only. So volume integral of rho v dv. Like this we can able to write. Now both sides we have volume integral only. Send this one this side, and if you remove that particular volume integral, what you will get, del dot d bar is equal to rho v. So this is also Gauss law only. We got this one from the integral form. So this is called point form. Point form of Gauss law or differential form of the Gauss law of the electric fields. Okay, so like this we have to consider. So I will write those two equations at one place. These are very important. Okay, so see here. So closed surface integral of d bar dot ds bar is equal to q enclosed. This is one thing, but basically from the definition we can tell the net electric flux passing through any closed surface is equal to the charge enclosed by that closed surface. From this we got this one, and now this one we have converted into point form, that is delta d bar is equal to rho v, and this itself we can able to write right side also integral form. So closed surface integral of d bar dot ds bar is equal to volume integral of rho v dv. So you can consider this one as integral form of Gauss law of the electric fields, and this is point form or differential form of the Gauss law of the electric fields. Okay, so these are very important. Okay, so next, now here we have one problem. We'll see this one. So okay, so point charges of q is equal to 2 power minus x square nano coulombs. Okay, this is the different point charges are there, and those values are given by some equation they have given. Okay, those are located on the x-axis at x is equal to 0, 1, minus 1, 2, minus 2, 3, minus 3. What is the net? This is not next. Okay, what is the net electric flux passes through the sphere of radius 2.5 meters? Okay, so sphere of radius 2.5 meters we have to consider, which is centered at origin. So anyhow, first we will find what are the charges they have given. So x-axis they said. So on the x-axis we have the locations 0, 1, 2, 3, and so on, and minus 1, minus 2, minus 3. But we have charges. How many charges? These charges are located at these positions. These positions. So how many positions are there? So how many positions are there here? 1, 2, 3. So 7 positions are there. So at each position one charge is available. That charge value is given by this equation. Okay. So when you take x is equal to 0, substitute here x is equal to 0. So 2 power 0 is 1. That means at x is equal to 0, we have the charge value that is 1 nanocoulomb. So I am writing that nano afterwards. Okay. So for the time being, you assume at x is equal to 0, we have 2 power 0. That means 1 nanocoulomb. Okay. All the charges are in the nanocoulombs. Okay. Remember that one. Next, at x is equal to 1. 2 power minus 1 square, that is equal to 2 power minus 1, that means 1 by 2. Okay, so at x is equal to 1, 1 by 2 nanocoulombs amount of charge is available. Next, at x is equal to 2, so 2 power minus 2 square, that is equal to 2 power minus 4, that means 1 by 2 power 4, that is equal to 1 by 16. So at x is equal to 2, we have how much amount of charge? 1 by 16 nanocoulombs amount of charge is there. Similarly, at x is equal to 3. At x is equal to 3 means 2 power minus 3 square, that is equal to 2 power minus 9, that is equal to 1 by 2 power 9. Okay, so this is some small value because numerator is increased. It is a small value. Okay, how much this one? I think 512. Okay, 2 power 10 means 1024. So 2 power 9 is 512. 1 by 512. So here we have 1 by 512. Now you take here x is equal to minus 1. Okay, x is equal to minus 1. Even though you are taking x is equal to minus 1, minus 2, minus 3, anyway here square is there. So same amount of charge you will get. So x is equal to minus 1 means 1 by 2. X is equal to 2 means 1 by 16. X is equal to minus 3 means you will get 1 by 512. So in this way the charges have been distributed on the x-axis. Okay. So this is a given thing. Now how much amount of net electric flux passes through the sphere of radius 2.5 meters? Okay, 2.5 meters means here 2 is there, here 3 is there. So this is 2.5, this is 2.5, and this is also 2 minus 2.5. So we have to take a sphere of radius 2.5. Of radius 2.5. Okay, so you assume this is a sphere. I did not draw properly. Okay, this is the sphere. Now within the sphere, how much amount of charge is there? Or simply you tell how many charges are there? 5 charges are involved, and remaining 2 charges which are situated at x is equal to 3 and x is equal to minus 3 are out of the sphere. Okay, now what we need? What we need in the sense, what is the net electric flux passes through the sphere? So it is a sphere is the closed surface. They are asking the amount of net electric flux passes through the closed surface. So the problem is related to Gauss law. So they did not mention apply the Gauss law. You need to understand this problem is related to Gauss law. So what is Gauss law? Net electric flux passing through any closed surface is equal to charge enclosed by that closed surface. So now the closed surface is the sphere. Closed surface is the sphere. So sphere, through the sphere, how much amount of flux is passing? That is exactly equal to, according to Gauss law, the charge enclosed by that closed surface. Enclosed means the charge should be there within the closed surface. That means within the sphere. So you should not consider the charges which are available at x is equal to 3 and x is equal to minus 3. So the answer will become 1. That means available at x is equal to 0, 1 by 2 available at x is equal to 1, and another 1 by 2 available at x is equal to minus 1 by minus 1, and 1 by 16 available at x is equal to 2, and one more 1 by 16 available at x is equal to minus 2. Okay, if you add all these things, you will get the answer that is equal to, if you take here, this is 1. So 1 plus 1 plus 2 by 16 That means 2 plus 1 by 8, that is equal to 16 plus 1, that means 17 by 8. So in this manner you will get what is this one? Now finally what is this one? Nanocoulombs. Okay, don't forget about nanocoulombs. This is the amount of flux passing through that particular sphere having the radius 2.5. So in this manner you can able to calculate. Okay. So just we have applied the Gauss law. Now there is another problem here. Uniform line charge densities. I have said that whatever the closed surface we are considering, in that closed surface you may have point charges, you may have line charges, you may have surface charges, you may have volume charges. You may have the combination of all these things also. So in the previous problem we have within the closed surface how many are there? Nearly 5. Okay, 5 point charges are there in the previous problem. Okay. Now, in this particular problem, they are talking about the line charges. So, uniform line charge densities of 20 nanocoulombs per meter lies on Z is equal to 0 plane. Okay, 0 plane, Z is equal to 0 plane means which plane that one? XY plane. So, X I am taking here, Y I am taking here. So, all are having the same line charge density, that is rho L is equal to 20 nanocoulombs per meter. Okay, and these are available at y is equal to 0. Y is equal to 0 means x-axis. Okay, so on the x-axis we have y is equal to 0. Okay, that means on the x-axis we have one line charge. Okay, next at y is equal to 1 we have another line charge, y is equal to -1 we have, y is equal to 2 we have line charge, -2 we have, and 3 we have, -3 also we have. So in this manner we have the line charges. Okay, now you see the remaining question. So all are having same amount of rho L, that is 20 nanocoulombs per meter. Now what is the net? What is the net electric flux passes through a sphere of 2.5 meters centered around the origin? Again, this part is same, similar to the previous question. Again, we have to take the sphere of radius 2.5. Okay, anyway, this is 3. So 2.5 will be here. You assume this is a sphere. Okay, this is -3. This is -2, -1, 0, 1, 2. So this is 2.5. This is also -2.5. Like this we have. Okay. So now this is the situation. How much amount of net electric flux is passing through this particular closed surface, that is what we have to calculate. You see here line charges are there. Okay, so this rho L is giving the charge per unit length. Okay, from here to here how much amount of here line charge, from here to here how much okay, I will change the color. From here to here how much amount of charge is there, from here to here how much amount of charge, from here to here charge we have to calculate, charge we have to calculate, charge we have to calculate. Okay, so if you can able to calculate the charge available within that particular sphere, same amount of electric flux is passing through that one. So I'm redrawing that one. See carefully. This is the closed surface. This is x is equal to 0. Sorry, this is x-axis means y is equal to 0. Y is equal to 1. Y is equal to -1. Y is equal to -2. And this is y is equal to 1. This is y is equal to 2. Like this we have taken. Okay, so this is actually y-axis. Just you assume like that. Okay, what is the radius of the circle? Sphere 2.5. So this is -2.5. This is 2.5. Okay, so that means this particular line I am giving the numbering here 1, 2, 3, 4, 5. Okay, this each line is having rho L is equal to 20 nanocoulombs per meter. Now first I will calculate for the first one. Okay, first line you assume. What is the length of the first line? It is actually diameter. Okay, so it is equal to 5 meters. For each meter, how much amount of charge is there? Rho L 20 nano coulombs per meter. So if you multiply these two, how much you are getting? 100 nano coulombs. So 100 nano coulombs is the charge available on this particular line. So on this particular line, how much charge is there? 100 nano coulombs. Now I am taking for the second line. How to calculate that one? Okay, this is 2.5. That's why we have calculated easily. But this one we don't know. This is surely less than 2.5. But how to get that one? You see here, this length we know that is 1, and this length also we know because it is a sphere. The radius is, this is radius only. So radius means again you have 2.5. But you don't know this length. You consider that length is x. Okay. So according to Pythagoras rule, what is that one? X is equal to square root of 2.5 square minus 1. This is the x length, and this side also x is there, that means 2x length. 2x you have to calculate, and this length is to be multiplied by 20 nanocoulombs per meter. Then you will get the charge available on this particular line. Same line is there here also. So line 4 is also same answer. Line 4 is also same answer. Now to calculate line 3 or line 5, okay, because line 3 length and line 5 length both are same. Here already I have written something, that's why I will take line 5. So from line 5 is nothing but what we have here. You can extend this one. You can extend this one like this. Sorry, like this we have to, from the origin we have to extend. Okay, I will change the color. So from the origin if you take, so this is 2.5, and how much is length is this one? This is 2. Magnitude is 2. So this one I am taking as, for example, k. So k is equal to, what is the value, which how much length will be there? Square root of 2.5 square minus 2 square. So like this will get, this is k, and total length is 2k. Okay, for 2k, that means if you take only fifth line, 2k into 20 nanocoulombs per meter, and for third line also same amount of charge is there. So for the first line, for the second line, third line, fourth line, fifth line, all the charges must be added. All the charges must be added, and same amount of electric flux is coming out of the sphere. So in this manner we have to calculate. Okay, this is simply the application of the Gauss law. Okay, if you have the knowledge on the Gauss law, this is just mathematical things we can able to do. Okay, then now electric flux density. Okay, already about d bar I have told clearly. Same thing, d bar is the electric flux per unit area, so measured in webers per, sorry, electric flux means coulombs, so coulombs per meter square. And if you recall your surface charge density, it is also coulombs per meter square only. So we have same units for these two. Okay, and as I said, electric flux is measured in coulombs. Charge is also measured in coulombs, and these two are also having the same units. Okay, d bar and rho s are also having the same units. Now vector differential surface at any point on open surface would be projecting normal to the surface. This one already I have told. Always the surface direction is perpendicular to it. This is the open surface like a screen, and what is the direction of this one? It may be coming towards you. Now you are sitting here, so the direction of the open surface is perpendicular to this one. That means it is representing towards you, or this is also perpendicular only, that means away from you. Okay, back side of the screen. So open surface means two projections are there, that means two directions are there, and always the surface direction is perpendicular to the surface only. So like this we can able to consider. But when you take the closed surface, okay, when you take the closed surface, remember this one, when you take the closed surface, always the direction is outside only. Okay, always the direction is outside only, that means only one side you can able to take. Okay, so vector differential surface at any point on the closed surface would be projecting outward normal. Okay, outward normal only. But when you take vector differential surface at any point on the open surface, we will be projecting normal to the surface. He said that normal to the surface, but he did not say outward normal. Okay, inward normal is also there. Okay, like that you have to consider. Now Gauss law in the integral form, point form already we have completed. Divergence in coordinate systems. Okay, why we have taken a divergence means because the point form of the Gauss law is involving del dot D is equal to rho v, so divergence is there. So I have given the formula, but once again I will write here. So divergence of d bar, for example. Okay, and d bar is given by it can be given in Cartesian, it can be given in cylindrical, it can be given in spherical. So in general we will take du u cap plus dv v cap plus dw w cap. So in Cartesian, u v w will become x y z. In cylindrical, it will become rho phi z. In spherical, it will become r theta phi. So rho v w means u v w means according to the coordinate system we have to change. And we know about the scaling factors h1, h2, h3. In case of Cartesian, 1 1 1. In case of cylindrical, 1 rho 1. In case of spherical, 1 r sin theta. Like this we will take. Okay, so what is the del dot d bar? It is equal to 1 by h1 h2 h3 dou by dou u of h2 h3 du plus dou by dou v h1 h3 dv, and continuation dou by dou w h1 h2 dw. So like this will be. Okay, this is del dot d bar. In any coordinate system, you can able to apply this particular formula. You will get related formula. Depends upon the problem, you can able to use the corresponding formula of the divergence. Okay. So electric field due to infinite line charge using Gauss law. Already we have done electric field calculation for the infinite line charge, and we got electric field is equal to rho l by 2 pi rho epsilon a rho cap. This is what we got. But this to get this one we have followed a Coulomb's law approach only. Okay, so we got this one by taking this differential charge we have taken, and we got the differential electric field, and we have integrated that one. Okay, so integral of what did we get here? Dq by 4 pi epsilon magnitude of r cube into r bar, and this dq we have written as rho l dl. This is the procedure we have followed, but here this is the lengthiest procedure. But instead of using this one, using the Gauss law also, we can able to get this equation very easily. You see here Gauss law means closure surface integral of d bar dot ds bar is equal to q enclosed. So this is the formula we have. Okay, now we can use this one. We can use this one to get this particular electric field calculation of the infinite line charge. So you see this is x-axis, y-axis, z-axis, same situation we have taken. So to apply this Gauss law, first we have to consider the Gaussian surface. First we have to consider Gaussian surface. What type of Gaussian surface we can take? Is it a sphere? Is it a cylinder? Is it a rectangle box? So what we have to take? And how to take means we have to take according to the symmetry condition. So what is the symmetry? From the line charge, the electric flux lines are going in all the directions like this. Okay, not only left side, not only right side. You need to assume that these are coming towards you also. Okay, like a bottle brush. You need to assume that it is like a bottle brush. For bottle brush, how the threads will be there. Okay, to clean the bottle, whatever the brush is there, how these threads are available, like that these electric flux lines are going outside. Okay, towards you also. Okay, in all the directions these electric flux lines are coming. So this shape is similar to what? This particular shape is coming in which shape? Cylindrical shape. So our Gaussian surface in this particular case is the cylindrical surface. So you take here cylindrical surface. Gaussian surface is the cylindrical surface. But if you assume one thing, now the cylindrical surface is having three surfaces, three open surfaces. One cylindrical, listen carefully, one cylindrical closed surface is equal to three open surfaces. Three open surfaces. One is top. I'm giving as one. Second one is bottom. This is 2. And third one is this curvature. Okay, cylindrical curvature. Okay, but if you observe one thing, through the top surface, no electric flux lines are going. So remove this one. Through the bottom surface also, no electric flux lines are going. Through the cylindrical surface only, we have this particular electric flux lines are passing. And how those are passing? Perpendicular to the cylindrical surface. What is the direction of the cylindrical surface? We know that surface direction is perpendicular to the surface. So this is the perpendicular to the surface, that is aero cap. In the same direction, our electric flux lines are also passing. That means D bar is having the direction only D rho aero cap. Okay, D phi A phi cap is not available. DZ AZ cap is not available. Generally, since we are working in a cylindrical coordinate system, D bar is given by D rho cap plus D phi cap plus DZ Z cap. But as we have taken the cylindrical surface and because of the line charge distribution, electric flux distribution, we don't have phi component, we don't have Z component. We have only rho component. We have only rho component. So D bar is equal to D rho aero cap, like that we have to take. Okay, D bar is equal to D rho aero cap, like that we have to take. So D bar is ready with us. And what is the direction of the DS now? Okay, so here I will write. So DS is the differential surface we have to take on the curvature of the cylinder. That is given by, we can able to tell, that is given by, because of the phase variation we will be having, so rho d phi, and because of the height we will be having, that is dz also. So this direction is aero direction. So ds rho in cylindrical coordinate systems, so ds rho, you can check your previous notes, whatever I have told in the previous classes, that is ds rho is equal to, this is a surface, and d bar is equal to, we can use d rho cap or aero cap, whatever it may be. Now if you perform the dot product in between these two, because here dot product is there, what will you get? So d bar dot ds bar is equal to, you will get rho d phi dz and d, like this you will get. Okay, d rho you will get. Now you apply this everything now. So closed surface integral of d bar dot ds bar is equal to q enclosed, that is equal to, so left side we have closed surface integral of rho d phi dz d rho is equal to, now what is the this particular thing we got? Charge is related to, we are working with line charge, that means dl, and integral of line integral of dz, because that is oriented in the z direction. So coulombs per meter into meter is coulombs only, so charge only will get. So now what we have here, d rho anyway it is fixed, and if you rho is also constant. Next d phi, integral of phi means with limits 0 to 2 pi will get 2 pi, and some height you consider, some height h will consider because of the integral dz, and it is equal to rho L is fixed uniform line charge density we are considering, and integral dz means we will consider some height h. So this height will be cancelled. Now d rho is equal to what you have, rho L by 2 pi rho. If you have d, you can calculate e, because d bar is equal to epsilon e bar. So e bar is equal to d bar by epsilon. So what will you get? Rho L by 2 pi rho epsilon aero cap. This is E bar equation. Same E bar equation previously we got using Coulomb's law. So now it may be somewhat difficult to you, because it is the first problem you are seeing using the Gauss law. Very simple thing. Instead of using the Coulomb's law, if you apply the Gauss law, it can be done very easily. Okay, that is what you need to remember. So you need to select the Gaussian surface in such a way that symmetry should be available with respect to the electric flux lines are coming from the line charge. So what is the symmetrical surface here? Cylinder we have taken. So cylinder direction, okay, cylindrical curvature, whatever the surface direction is there, that direction, and the electric flux direction, that means d bar direction, both are in the same direction. That is the advantage of this particular Gauss law. Okay, what is the advantage of the Gauss law? Means the direction is same. Okay, so this integral part will become very easy. But integral part is somewhat difficult in case of Coulomb's law application. But integral part will become very easy because we have selected the Gaussian surface in such a way that The directions of the electric flux and the direction of the electric flux density both are in the same directions, or both are in the perpendicular direction. If it is perpendicular, surely 0 will get. If it is same direction, maximum will get. With that logic, we are applying this particular Gauss law. So line charge is over using the Gauss law. Similarly, you can able to go for the surface charge. So in this case also, surface charge is available on the xy plane. XY plane. So what is the Gaussian surface means? Again cylinder you can take. So I am taking one cylinder like this. So now through what part of the cylinder this Gaussian electric flux lines are passing? That is what you need to observe. When we have taken the line charge, okay, line charge with Gaussian surface, the flux lines are passing through the curvature cylindrical surface, but not through the top surface, but not through the bottom surface. But in this case, for the sheet charge, how the electric flux lines are passing? Perpendicular to the sheet. That means through this particular top surface, the electric flux lines are passing. Through this bottom surface, electric flux lines are passing. Okay, not through the curvature surface of the cylinder. So this is what you need to understand. So when you take this closed surface integral of d bar dot ds bar is equal to rho s ds, actually q enclosed. So that is rho s ds we can take. So what we can able to take here, d bar is dz az cap, and ds is nothing but simply this particular surface. That surface is given by, because of the changes in rho, because of changes in phi, rho d phi, and direction is given by z direction. You can take the dot product in between these two, you will get 0. But if you take only this one, you are covering either upside or downside, so you have to take two sides. Okay, that's why you will get 2 in the denominator of the E bar. So simply with this particular application, you will get E bar is equal to rho s by 2 epsilon perpendicular to this one n cap. Like this you will get. So same derivation we can able to perform very easily by considering the proper Gaussian surface like that. Okay. So now we have here another problem. We'll see this. So in a certain region, magnitude of electric flux density is proportional to R power K. This is R power K. What they have given, electric flux density is proportional to. So electric flux density, magnitude of electric flux density is proportional to R power K. Okay. Assume flux density is projecting in a radial direction. That means dr ar cap. Like this we have to take. Radial direction means you can take, this is in the spherical coordinate system. Actually spherical coordinate system is dr ar cap d theta a theta cap plus d phi a phi cap. Since in the question itself they have given clearly that the electric flux line is passing in the radial direction, so you no need to consider this one. So the problem has been simplified. Okay, so now what we have to take, assume the flux density is projecting in the radial direction. Okay, select the value of K such that the electric flux density has 0 divergence. Okay, so they have given the condition, that is del dot d bar is equal to 0, divergence is equal to 0, so that we need to get the value of K. So anyhow this d bar is now can be written as, by removing this proportionality we will get the proportionality constant. You assume some C1 constant. Okay, C1 into R power K. So this is what we have, d bar. Okay, so now we need to use d here R cap also we need R cap. So this is our d bar. Using this one now we are going to get this k value. K value we have to identify. So for that we are taking this delta d bar is equal to 0. Since we are working in the spherical coordinate system, we need to write the divergence formula in the spherical coordinate system. First I will write the general formula. So 1 by h1 h2 h3 dou by dou u, and what is this one, h2 h3, and here we have du. This is the formula. And further we have dou by dou u and dou by dou w. Anyhow we have only radial direction, that means only first component is enough. So 1 by h1 is 1, h2 is r, h3 is r sin theta. So 1 by r square sin theta into dou by dou r, h2 h3 is r square sin theta du is nothing but now we have C1 r power k. Okay, so this itself is our dr or du. Okay, so this is what we have. Now it is equal to 1 by r square sine theta. We are doing the differentiation with respect to r. That means the sine theta is constant. So C1 is constant, sine theta is constant, dou by dou r of r power k plus 2. Like this we have. Okay, now they said that divergence is equal to 0. Okay, divergence is equal to 0. So we have made this is equal to 0. Send this everything to the right side. So you will get this dou by dou r of this one is equal to 0. Now perform the differentiation here. You will get a k plus 2 into r power k plus 2 minus 1. It is equal to 0. So the product of two terms is equal to 0 means either this one is 0 or this one is 0 or both are 0. So if you take k plus 2 is equal to 0, you will get k is equal to minus 2. Okay, so in this way we have calculated k is equal to minus 2. Okay, okay, next term. Okay, here we have another problem. Let vector d is equal to r by 3 comma 0 comma 0, r by 3 comma 0 comma 0 in spherical coordinates. Okay, that means d bar is equal to, we can take r by 3 into ar cap, remaining two are zeros only anyway. Find the amount of flux passing through a sphere of radius 1 meter, center data origin. Okay, this radius is 1 meter. Through this one, how much amount of flux is passing, and find the charge enclosed within, and also indicate whether the electric flux is leaving or entering. So simply you calculate delta d bar first, that is equal to rho v. Then you can able to understand how much charge is there. Okay, so already just in the previous formula problem only we have taken the formula, that is 1 by r square sine theta dou by dou r, here r square sine theta, here dr. This is what we have to apply. Anyway, here also d bar is having only radial direction. Okay, so what we can write here, 1 by r square sine theta, and this is sine theta, we can take outside, so dou by dou r, but we have r square and dr is nothing but r by 3. Okay, so this is what we have. So sin theta is cancelled, so 1 by r square, it is 1 by 3 also coming outside, this is r cube, so 3r square is the derivation of this r cube. So what we have here, it is r square means we got 1. Okay, we got here 1, that means delta d bar is equal to 1 we got, that means rho v is equal to 1 according to Gauss law. So what we need here, find the charge enclosed. So if you have rho v, how to calculate charge? So charge is equal to integral rho v dv. So it is equal to integral 1 dv. So what is the volume? Volume of the sphere. Okay, volume of the sphere you have to take, that is 4 by 3 pi r cube. So in this way you get. Okay, and it is a positive charge, so the flux is leaving. It is a positive charge, so that the flux is leaving. Like this you can able to assume. Okay, positive charge, so that flux is leaving. Next, so again next problem you can able to do this one. Let vector d bar is equal to the now they have given in Cartesian coordinate system. So d bar is equal to 4x cube. So it is 4x cube x cap plus 3xz y cap plus x square y z cap. Okay, and they said that it is nano coulombs per meter square. Okay, here some mistake is there, it is meter square. Okay, so find the total charge enclosed within the closed surface enclosed by the limits 0 less than x less than 1, 0 less than y less than 1, 0 less than z less than 1. Also find the amount of electric flux passing through this closed surface and indicate whether the flux is leaving or entering. Positive means leaving, negative means entering. Okay, that is simple only. Again, same procedure. You find now first del dot d bar and write the formula in this Cartesian coordinate system. You will get rho v. Okay, here substitute here. Find this is rho v. Then to get charge, you need to apply volume integral of rho v dv, where x, y, z are changing from 0 to 1. Very simple thing. If it is positive charge, leaving. If it is negative charge, entering. Okay, that is what you have to apply. Now the next problem. D bar is equal to 20 by rho square into something is there. Now not this is not a cubic meter. Okay, meter square. Next, find the net charge within the closed surface defined by. Again, same problem, but they have given now in which coordinate system? Cylindrical coordinate system. First, write this divergence formula in cylindrical coordinate system. Solve this one, you will get rho v. Then again, this q is equal to volume integral rho v d. Okay, and these limits you have to apply. Okay, that's it. You will get the answer for this one also because same thing is there. Now the next concept is work and potential. Okay, work and potential. We'll see this one. Till now, do you have any doubt before going to the next topic? Hello, hello. Are you getting what I'm telling? If you have any doubt, you can ask me.
No, sir.
Okay, can I continue?
Yes, sir.
Okay, okay. So now we'll see. Next topic is work. So now listen carefully. Simply, work is nothing but force acting over a distance. Force acting over a distance. That means here two things are required. One is force, second one is movement through a distance. Okay. So there should be a movement. That means a distance. Movement is there means the distance is coming into the picture. Okay. So through how much distance the object has been moved, like that we have to consider. Okay. So that is called work. We can say work was done when there is a force acting over a distance. Then, so work is equal to force into distance. But if you see the equations of the work, you will be having here negative symbol. Okay, and you will be having dot product between length vector and force vector. And sometimes you will see like this. This is the actual equation we are using. Okay, if you remove this integral, you will get a differential work because of the differential distance. If you integrate this one, you will get W. Okay, y dot product is required again. Okay, already we have seen the dot product importance in case of the Gauss law. Again, same importance will be there. So y dot product is there. Okay, y differential length means that is common thing. For example, this is the moment. We are not calculating the entire moment at a time. We'll calculate through dl first. Then we'll integrate to come up to here. That's it. Okay. This is due to this one small differential work is there. To get the total work, you have to integrate. Then you will get a total work. That is common thing. But why do we have the dot product? That is very, very important. So before entering into that one, so in general sense, we can say why negative symbol is also there. That is also very, very important here. These two things you have to understand very carefully. Now listen carefully. For example, one person is there. Okay, he is holding in his hand. He is holding one dumbbell. Okay, one dumbbell he is holding, and another person is there. He is moving this particular dumbbell upside and downside. Okay, so even this is the first person, this is the second person. Okay, generally what will happen? The first person also is using its energy. First person is also using his energy in order to hold this one. For example, 1 hour amount of time he is holding that one. So he is expending certain amount of energy. Okay, in order to hold that particular dumbbell. Okay, in order to hold that particular dumbbell, he is expensing some amount of energy of him. Okay, he is losing his energy in order to hold that particular dumbbell. In the second case also, he is keeping this particular dumbbell upside, moving the dumbbell upside for some time, then bringing that dumbbell downside for some time, again upside, again downside, again upside, again downside. Like this he is working. And here also he is spending certain amount of energy. Okay, but according to physics, the work was done by the first person is 0, by the second person is not equal to 0. Why? Why the first person work is equal to 0 means, first thing is there is no movement. Distance is equal to 0. Distance is equal to 0. So that we can able to tell work is 0. If you simply hold there, according to physics, there is no work was done. Okay. But in the second case, movement is there. So that we can able to tell work is there. Okay. So distance is not equal to 0 in the second case. And one more thing. Always the dumbbell is going upside means work is there, because it is opposite to the earth gravitational force. Okay, whatever the force applied by the person is opposite to the gravitational force. If this should be there like this. Okay, it has to applied in the opposite way. Then only maximum amount of work can be done. Okay, that's why we have the negative symbol. Because of this opposite nature, we have the negative symbol here. So one reason is over. Negative symbol. Why we have to put the negative symbol is over. Why distance is required, that is also over. Now we will see why the dot product is required. Okay. So you assume here one box is there. Okay. One box is there. Here one person, he is pushing this box in this direction. The box is also moved in this way. So force has been applied. Movement is also there. That means distance is there. Okay. So in which direction force has been applied, in the same direction the box has been moved. That means how much angle is there? Same direction means theta is equal to 0. Now here box is there. Okay. Here person is there. He is pushing this particular box downside. But there is no movement here. There is no movement means distance is equal to 0. So that work is equal to 0. But here work is not equal to 0. This is one example. Now I will take another sheet. Now you see. You take one trolley bag. One trolley bag is there. This is the ground or road, whatever it may be. Road. So you are standing here and holding the trolley bag. Okay. So using this particular trolley bag handle, you are holding that one and moving this side. Actually, you are applying the force in this direction. You are applying the force. You are pulling this bag towards you. That means in this direction. But movement is there in this way. Movement is there in this way. DL bar direction is in this way. So the F bar direction and DL bar direction is making certain amount of angle theta. Okay, it is making certain angle theta. So this is F bar. This is DL bar, making certain amount of angle. Okay, now what is the product of force and distance? We have to take force multiplied with the distance. This is our work formula. Are you utilizing the total force in pulling this particular trolley bag? No. When you have this is a situation, you are not expending that much amount of force compared to when the bag is there like this. It is not a trolley bag now. It is not trolley bag. You are pulling this one this side and it is moving this way. Force is in this direction. DL bar is also in the same direction. Now theta is equal to 0. Here theta is equal to, for example, 45 degrees. Okay. So what you are understanding here? When angle is equal to 0 between force and the distance, here more force is required. Na? In order to pull the bag, large force is required. But when you have the trolley bag like this, when you are making certain angle with respect to ground and pulling the bag in this way, you are not expending that much amount of force compared to this case. Okay, if it is F1, if it is F2, F2 is always lesser than F1. Situation is same, pulling the bag only. But when you are pulling the bag by making certain angle with the distance, that means movement vector, distance vector, DL bar vector, then amount of force acting in order to pull the bag is lesser compared to the situation where angle is equal to 0 in between force vector and the distance vector. So this is okay in words. I have explained the situation in words. This is okay. But how to keep this one in the mathematical form? How to keep this one in the mathematical form means now the cosinusoidal function will come into the picture. You see, when the angle is 0, maximum force is required. But when the angle is non-zero, force is reduced. Force is reduced. When force is reduced, the work is also reduced. Okay. So this is situation 1, this is situation 2. In situation 1, since angle is 0, work is equal to F bar dot DL bar dot. Okay, why we have taken dot? R. Product of F bar DL bar cos 0, like this I can take. Maximum force, maximum angle. Sorry, angle is 0. In the second case, if you take magnitude of F, magnitude of DL, and here cos 45. Cos 45 means what? 1 by root 2. So you see work is reduced because force is reduced. 1 by root 2 we got here. Okay. Actually this is because the projection we have to take here. Okay. It is actually F cos theta. That F cos theta is multiplied by DL. Like that only this work equation we got. So there is a requirement of dot product now. You can see here cos, this cos is making the dot product. So this W bar is equal to minus integral F bar dot DL bar. So in this way we can able to take work equation. Work is the vector. Sorry, work is the scalar. Dot product na dot product resultant is scalar. So work is the scalar. In this way we can able to have the equation. Okay. So now from the Coulomb's law we have F bar is equal to the relation between F and E, that is Q E bar. Substitute this one in the work equation. So you will be having like this. Work is equal to minus 2 times of E bar dot DL bar. This one also you can able to use. Okay. That is a requirement of the dot product in the equation of the work. Now here find the work in moving a charge of 5 microcoulomb from origin to 2.2 comma minus 1 comma 4 through the field E bar is equal to something they have given via the path 0 0 0 to 2 0 0 to 2 minus 1 4. Okay, we have to find the work in moving a charge. Okay, so whatever I have explained the examples, so those are mechanical examples. So trolley bag, okay, one box, all those things are mechanical examples. But in our context, what is force? Okay, we are moving not the trolley bags, we are not moving in our context, we are not moving the boxes, we are moving the charges. So one charge is there Here another charge is there. You take it is a test charge, and here another charge is there. Because of this charge Q, anyhow, here we have electric field. That means electric flux lines are situated throughout this particular screen. That means throughout this area. So here electric field is available. Already electric field is available. So we are bringing this QT. We are bringing this test charge QT from some point to another point. That point is available in the field of Q. Okay, this is A. We are bringing the charge QT from B. Okay, so this is the path. We are bringing the test charge QT from point B to point A, but point A is there in the field of Q. In the field of Q. Point A is there in the field of Q. And how we are moving? In the opposing way. Field is there towards QT, but we are moving in the opposite direction of the field of Q. That's why minus symbol is coming in front of the work. Okay, then only work is said to be done. Like that we are taking here. Okay, so this is a situation when you move the QT, we can able to tell work was done in moving the charge QT. Okay, from where to where? They said that from origin to the position 2 comma minus 1 comma 4. But this 2 comma minus 1 comma 4 is there in the field E bar is equal to 2xyz x cap plus x square z y cap plus x square y z cap. Okay, this is the E bar. So we are moving from 0, 0, 0 to this 2 comma minus 1 comma 4. But actually we are not moving directly. Okay, they have given the path also. Okay, they have given the path also. What is the path? 0, 0, 0 to directly we are not moving to 2 minus 1, 4. First we are moving from 0, 0, 0 to 2 comma 0 comma 0. And from this we are moving to 2 comma minus 1 comma 0. And then we are moving to 2 comma minus 1 comma 4. So in this manner we are moving. 0, 0, 0 to 2, 0, 0. And then 2 minus 1 0 and then 2 minus 1 4. So in this path the charge is moving. Okay, we are moving that particular charge. So in this particular movement, how much amount of work was done, that is what we have to calculate. So for that purpose, what is the equation we have to take? Already we know W is equal to minus integral Q, this is E bar dl bar. Okay, so which charge we are moving? 5 microcoulomb. So this one already they have given, sorry, 5 microcoulomb, and E bar also they have given dl bar. But here the path is we are taking not directly. The path is from here to here, this is the first path. From here to here, this is the second path. From here to here, this is the third path. And if you see very carefully, in the first path only x is changing. Okay, only x is changing from 0 to 2, and in this path y is 0 and z is 0. This observation is important. You see how small things these are, but these are important to do the problem. Next, in the second path, you can able to take y is changing from 0 to minus 1. Okay, y is changing from 0 to minus 1. Okay, but x is fixed at 2 and z is fixed at 0. Okay, and in the third path, z is changing from 0 to 4 and x is fixed at 2 and y is fixed at minus 1. Okay, you can able to split this integral. W is equal to minus q times of path 1 E bar dot dl bar plus path 2 E bar dot dl bar plus path 3 E bar dot dl bar. Like this we can split the integral. Okay, so in the first path x changes from 0 to 2 and y is 0, z is 0. Okay, now this is the E bar equation. Since x is changing, dl bar is equal to dx x cap. Okay, so E bar dot dl bar means E bar is having only, now we have to consider only x component only. This is the component we have to consider, because dot product we have to perform with dx x cap. Okay, x cap means here we don't have y component and z component. X cap dot x cap means we will get only x component of the E bar. So now the E bar dot dl bar, clearly I will write E bar dot dl bar is equal to 2xyz only. But as per this, y is 0, z is 0. If you substitute here, you will get 0. So in the first path, we got first integral is equal to 0. Because E bar dot dl bar itself is 0. So first integral is 0. Now we will see the second path. So in second path, y changes. Okay, in the second path, y changes. So dl is equal to, we have dy y cap. So what is the E bar dot dl bar now? Y component we will get. That is x square z dy, x square z dy. But in this case, z is 0. So if you substitute z is 0 in the second path also we have got integral is equal to 0. Integral is equal to 0. Now in the third path, z changes. That means dl bar is equal to, we have dz z cap. So E bar dot dl bar is equal to, only z component we will get na, that is x square y. X square y, and x is equal to 2, that means 2 square is 4, y is equal to minus 1, that means minus 4. So E bar dot dl bar is equal to, we got minus 4. So now work equation, if you take only the third integral we got na in this particular formula, because first two integrals became 0. So work is equal to minus q. Q means how much they have given, 5 micro. Third integral we are doing where z is changing from 0 to 4, and E bar dot dl bar we got, how much we got, E bar dot dl bar we got we got minus 4 dz, minus 4 dz, like this we got. Okay, so it is equal to, minus into minus is plus, and 5 4 is 20, 20 micro into 4. Okay, integral of dz means 1 z. If you substitute the limits, we will get 1 more 4 we will get. So 15 5 is 16 5 is 80. 80 micro. Work means what are the units? Joules. 80 microjoules we got. Okay, practice this problem so many times. Okay, then you will get the clarity. From the problems, you will get the knowledge. Okay, in the EMTL subject, how we can able to get the this particular knowledge means through the problems also we can get. Even though the theory concept you may not understand in a depth way, by solving several problems, you will get the knowledge. Okay, but those problems must be taken from the good textbooks. Okay, like Sadiku you can take, Heath you can take, the scams outline series you can take. Okay, so by solving the problems, you will get the knowledge here. Okay, so if you see the next problem, repeat the same thing but path is changed. Okay, so what is the meaning of this one? We are moving the charge, for example, from point A to point B through this particular path. This is path 1. Now we got work is equal to 80 joules. Okay, now what will you do? You move the same charge, but we are changing the path now. This is the second path in path 2. So in path 2 also you will get the same amount of work, that is 80 joules only. So for this question also answer is 80 joules only. So this is very very important. So in our electrostatics, the work depends on work done. Okay, work done depends on end points of the path only, whether it is from A to B or not. That is what it will see. Okay, end points only, but not on path. Okay, in which path you are moving the charge, that is not important. What is important? From where to where you are moving the charge, that is important. From point A to point B you are moving the charge, that is important. But from through which path you are moving, that is not important. For example, for your understanding, x y. Okay, here two paths we are taking. Okay, so this is O A B. Okay, OAB, this is the path. From O to A, first you will move the charge, and from A to B, next this is the second path. Okay, so otherwise if you move like this directly, OB. So this is path 2 and this is path 1. You will get the answer is same. Work is equal to same thing you will get. In both paths you will get the same thing. That means what here what we have to consider, it starts from O and ends at B. That is the thing. It is not depends upon the path. Okay, in which path you are moving the charge, that is not important. What is important, from where to where you are moving the charge, what is the starting position, what is the ending position, that is important here. Okay, so you try to solve this problem by substituting wherever it is required. Whenever you are doing the integration with respect to x, change everything into x. Okay, whenever you have y, substitute minus x by 2. Whenever you have z, you can take z is equal to x. Everything is converted into x, so you can do the integration. When you want everything in the y terms, so wherever x is there, you can write minus 2y. Wherever z is there, first you write 2x and x can be written as minus 2y. Everything can be converted into y terms. If you need only z terms, everything can be converted into z terms using these relations, and you can able to calculate the integral, so that you can calculate the work done. Same 80 joules only you will get. Okay, so in this way you can able to do the work done problems. Okay. Okay, it's already 8:34. We'll stop today, and rest of the things we'll see tomorrow. Okay, tomorrow we can start the magnetostatics. So most of the electrostatics topics are over. Electrostatics only will take time, because everything we have to tell new things. But once it is completed, similar to this one only, we are comparing and reading about the magnetostatics. So it will not take that much amount of time. Okay. Okay. Anyhow, if you have any doubt till now, you can able to ask. Otherwise, we'll close the session. Hello. Hello.
No, sir.
No doubt, sir.
Okay. Okay. Closing. Okay.
Thank you.
Okay. Thank you.
Thank you, sir.
Okay. Okay.